Since data forms space and we are already familiar with distance and similarity measures, we can find points near a given point. Finding points near a given point is called computing the nearest neighbors. Given a data point, finding k closest points is called the computation of k nearest neighbors. Today, we will discuss how to find k nearest neighbors of a given point. We will work on a Python code after we learn the theory. Hi, I'm Dr. Shahriar Hossain. You are watching one of the videos of the Data Science Lecture series on computingforall.com. Let's talk about k nearest neighbors. Finding k nearest neighbors is also known as computing the KNN. Here is the problem statement. Given a vector x and a dataset D, our target is to order all the vectors of D in such a way that the distance between x and a point in the ordered list is always smaller than or equal to the distance between x and a point that appears later in the ordered list. KNN returns the first k vectors of that ordered list where k is always smaller than or equal to n. N is the number of data points we have in dataset D. To make a program efficient, KNN returns the indices or the row serial numbers of the top k nearest neighbors instead of returning k complete vectors from the data. The distance function can be any proximity function that we are already familiar with from the previous lessons. We might need a distance measure for certain applications. For other applications, a similarity measure might be all right. Let us take a look at an example. The table on the left side of the following figure has 8 rows or objects and 2 columns or features. A point x equals, let's say, 13, 17 is provided. This point 13, 17 is the given point against which we will compute the nearest neighbors. Let us assume that we are attempting to find 4 nearest neighbors of x from this data table. Notice that in the table we named the rows with row 0, row 1, row 2, so and so forth. We have 8 rows, therefore our row numbers or row IDs vary from 0 to 7. Now, why are we starting our row IDs from 0? We are starting our row IDs from 0 because in Python programming language, array indices start from 0. Since our dataset will be considered a two-dimensional array in Python, the first row will have an index of 0. So that the coding does not become confusing, I am using row index starting from 0 here. Also, I am using indices 0 and 1 for two features. That's why I have feature 0 and feature 1. It is just a programming semantic. In another programming language, the index might start from 1. Such as, unlike Python, MATLAB has indexing of arrays beginning from 1 instead of 0. Anyway, we will be using Python, so we are using indices or row IDs starting from 0. Again, x 13, 17 is a point whose nearest neighbors we want to find. Before we go for the actual computations, let us see how the space looks like if we plot these rows as points in the space. Let us consider feature 0 as the horizontal axis and feature 1 as the vertical axis. Here are all the points. Notice that row 0 contains 5, 2. Here is row 0 in the plot. Row 1 contains 1, 3, and here is the point. Row 7, that is the last row, contains 10, 12. Here is the point. Each row is a point here in the space. From previous videos in this lecture series, note that we are able to draw such a plot for one-dimensional, two-dimensional, and three-dimensional datasets. For higher dimensional data, we cannot plot the points like this because our visualization capacity is limited to 3 dimensions. Still, please do remember that the space exists for any number of dimensions. We can compute distance between higher dimensional points using the distance formula such as Euclidean distance and Manhattan distance. Since we can compute distance between data points, we can always find the nearest neighbors given a point. Anyway, in this example, we have two-dimensional data. Therefore, it is easy to visualize the data in the 2D space. Our reference point is 13, 17. Again, 13, 17 is the point whose nearest neighbors we will find. Plotting 13, 17 on the two-dimensional space, we see that points for row 4, row 5, row 2, and row 7 are close. If we are attempting to find 4 nearest neighbors, then these 4 points are the nearest neighbors of the point 13, 17. We have found 4 nearest neighbors of the point 13, 17 using the visual representation. Unfortunately, if we had 4 or more columns in the data, this process of visually detecting nearest points will not work. Therefore, we need a computational method for which I can write a program that will find the nearest points. To compute the k nearest neighbors of the given point x, 13, 17, we first compute the Euclidean distance between x and every row in the data. The row or the data point that has the smallest distance is the first nearest neighbor. The data point with the second smallest distance is the second nearest neighbor. When k is equal to 4, we select the rows for the first, second, third, and fourth nearest neighbors in ascending order of the computed distance with x. Calculations for Euclidean distance of 13, 17 with all the rows are shown here. Notice that row 4 is the first nearest neighbor because it has the smallest distance. Row 5 is the second nearest neighbor because row 5 has the second smallest distance with the point 13, 17. So and so forth. A KNN algorithm with k equals 4 will return an array with row indices of 4 nearest data points. In this example, the 4 nearest neighbors are row 4, row 5, row 2, and row 7. Hence, the KNN algorithm will return the list 4, 5, 2, 7 that contains the indices of the nearest neighbors of 13, 17. The indices are ordered based on the ascending order of the distance between the row and the given point 13, 17. We have used this example of two-dimensional data because it is easy to visualize two-dimensional space. In reality, the data can have any number of dimensions. To use Euclidean distance to compute k-nearest neighbors, the given vector x must have the same number of dimensions as the data. Let us discuss a Python implementation for computing KNN from scratch. We start by importing NumPy. We will write a function for finding k-nearest neighbors. For this function, as parameters, we need the vector for which we will compute the nearest neighbor. We also need the entire data table in which we will look for the nearest neighbors. And finally, we need k, the number of nearest neighbors we are going to return. To compute nearest neighbors, we will need the Euclidean distance between a pair of vectors. Let us write a different function named Euclid for that. Given two vectors, we write the code to compute the Euclidean distance using the formula that we learned in a previous video. Let us get back to the k-nearest function. We'll compute the Euclidean distance between the reference vector VEC and each data point in the data table using this loop. There will be two columns in the results variable. The first column will contain the row indices. The column will contain just 0, 1, 2, 3, up to n minus 1, where n is the number of rows in the data table. That is, the first column of result will contain all the data row indices. The Euclidean distance between the reference vector and each row is recorded in a cell of the second column of the result variable. Note that row index 0 of the second column of a result stores the distance between the reference vector and row 0 of data. Second column of a row with index 1 stores the distance between the reference vector and row 1 of data, so and so forth. After the loop is executed, we will have all the distances. But now we want to sort the rows of result based on the distance column. We use the Python function named sorted, where we say how the sort key will be used. We mention that the second element, that is index 1 of any row, will be used for the comparison purpose because we know that in the result variable, column index 1 contains the distance. After the execution of sorted, we will have the sorted result. Rows of a sorted result are now sorted based on the distance values stored in column 1. The indices that we stored in column 0 now contain the indices of the nearest neighbors in order of their distance with the reference vector. If k is less than the number of rows in the data, then we select top k indices from column 0 of the sorted result. If k is greater than or equal to the number of elements, we just return what we have in column 0 of the sorted result variable, because column 0 contains the indices of the nearest neighbors. We return the indices. That's it. We have our nearest neighbor function. Let us first use the same two-dimensional data that we used to explain the theory. I create the data in a NumPy array. Let us say that 13, 17 is our reference vector. Let us call the k-nearest neighbor method that we wrote with the following parameters: the reference vector, data, and k is equal to 4. Let us print the returned indices, that is, the indices of the nearest neighbors in the data. After running it, we see that rows 4, 5, 2, and 7 are the 4 nearest neighbors of the reference vector 13, 17. Now let us change the dataset a bit. Let us make it a 5-dimensional dataset. That is, it will have 5 columns. Let us say that our reference vector is row 0. That means we will find the nearest neighbors of row 0. If we run this, we see that the 4 nearest neighbors of row 0 are row 0, row 4, row 2, and row 6. If you are wondering why do we have row 0 as the first nearest neighbor of row 0, that is because our reference vector is row 0 and the distance is computed with all the rows, which include row 0. Therefore, the distance between our reference vector and the actual row 0 is 0 because they are the same vector. Similarly, if we make row 2 our reference vector, notice that row 2 is its first nearest neighbor. Again, that is because our reference vector is nothing but a copy of row 2 now. Therefore, row 2 is the first nearest neighbor of row 2. Instead of writing the code to find nearest neighbors from scratch, we could use scikit-learn, which is a machine learning package available with Python. The function nearest neighbors can be used from sklearn.neighbors. We call the function with k equals 4. This nearest neighbor function has the ability to organize the vectors in the data using a special data structure to make searching for nearest neighbors faster than the brute force search that we used in our previous code. One such special data structure is called a ball tree. We are asking the nearest neighbor function to use the ball tree data structure to organize the rows of the data table so that searching for nearest neighbors becomes easier later. The fit function will use the data matrix to create the model. The model will be returned in the variable nbrs. Now, all we have to do is ask the model to return us the nearest neighbors of a reference vector. Here, we provide a reference vector which is exactly row 0. We could give arbitrary number of reference vectors using a matrix in this parameter. That is, this parameter is able to take a matrix of reference vectors, nearest neighbors, and distances of each of the rows of this matrix will be computed. In this example, we are only providing one vector as our reference vector, which is just the content of row 0. The k-neighbors function returns two things: the distances and the indices of the nearest neighbors. Since we have only one reference vector and our k is 4, there will be 4 distances and indices of 4 rows in the indices variable. We print the indices and the distances. Once we execute the program, we will see that row 0, row 4, row 2, and row 6 are the nearest neighbors of our reference vector, which is row 0. Obviously, since the reference vector is row 0, the first nearest neighbor is row 0. The distance of the first nearest neighbor is 0 because the distance between two vectors with the same content is 0. Row 4 has a distance of 2, from the reference vector. Row 2 has a distance of 3.46410162 with the reference vector. Finally, row 6 has a distance of 3.87298335 with the reference vector. We can change our reference variable to any other row, such as row 3. Obviously, row 3 is the first nearest neighbor of row 3 because they are the same vector. The distance is 0. The second, third, and fourth nearest neighbors are respectively row 4, row 1, and row 2. Corresponding distances are here. Computing nearest neighbors is one of the fundamental tasks most widely used in data science, especially in data mining and machine learning. One common application is classification. Classification is a topic that we will discuss in the future. For now, please know that given an object, KNN can help us find objects closer to the given object. In a large dataset that contains millions of data points, it can help us find objects similar to a given object efficiently. Instead of using ball tree, we could use another data structure called KD tree. For small datasets, we can use the brute force strategy, which we wrote first. We can also tell scikit-learn to use the brute force strategy by stating the syntax brute here. We also have the option to tell the model to choose the most appropriate data structure based on the data passed to the fit method. For automatic selection, we use the word auto here. To keep things simple, I would suggest to use either ball tree or KD tree for any size of the data. In the description, I will provide a link with the codes that I wrote today. I hope you found this video useful. If you enjoyed the video, subscribe to this channel so that you receive a notification when we publish any new video. Wish you a wonderful time.